Hey guys, on the layout of the basically, I am going to introduce to you to the second law new property, which is called the entropy. Previously, in chapter number 6, when you learn about the second law, basically we have yet to learn or even to make use of the new property which is called entropy, which is interrelated directly with the second law. So here in this chapter, we are going to make use of entropy from time to time, and also we are going to extract data from the thermodynamic. Okay, in this chapter also, we are going to learn how can we simply learn about what is actually entropy principle, and how can we simply calculate the entropy change during a process or even during a cycle, right? So different type of substance basically will make use of different type of formula already on the entropy change. And for example, if you have like a compressible substance for liquid and solid, have a special formula for entropy change. Whereas if you have gases that behave like an other gas, they also have their own formula, and also they have also their own like some sort of method to solve entropy change of that particular gas. And we also going to learn what we call it as isentropy process. This is a very special term where you're going to encounter from time to time or even right after this chapter. And how can we make use of this isentropic process, and we apply the entropy balance on various systems. Okay, so before that, let us do some very simple quiz, guys. Uh, um, which of the following can be considered as an application of entropy principle? Answer A, transfer of heat through a finite temperature difference. B, mixing of two fluids. C, maximum temperature obtainable from two finite bodies. Or D, the answer is all on the above. Yeah, let me start on a poll, right? So guys, you can start trying to answer on that. Mm, yes, repetition. Okay, majority of you say the answer is D. And some choosing A, B. Or C, quite surprising. So actually, uh, the answer should be all of the above mentioned, because you recall, you have been from the previous chapter 6 the other day. Mm, what we accompany about the yeah, we know that this present actual processes. Okay, no matter how we try to match the irreversibility is also there. Now we talk about irreversibility. Actually, it is towards second law of thermodynamics, which is later on as entropy. So can cause irreversibility of okay. So this is one of the reason why you're going to have like DTU is very small or even almost approaching towards zero. Okay, so this is how actually a system can be considered as reversible. That means this is almost like approaching the ideal part of the process. Now, mixing of two fluids, and this is one again common example. If you check from the lecture notes, this is one of the common example pertaining it. And of course, maximum temperature obtainable from two finite bodies. This like almost similar to your punya answer A. So here, that's why, as you can see, A, B, and C, they are all applicable with the second law. So that's why the answer should be D. All right. Okay, now, when we talk about second law, and then from the first chapter during the new semester the other day, we have looked at on the second law expression, where it is called as a quantitative measure of microscopic disorder of a system. The keyword here is disorder, right? So entropy actually is a measure of energy that is no longer available to perform useful work within the current environment. And for example, if you have like atmospheric air or circulation air, which is we have not yet to extract or make use of the energies within the surrounding air, right? So that energy within the surrounding air can be classified as microscopic disorder, and it is can call as entropy, right? So that's why to obtain the working definition, right? So we have to make use of the second law, eh? And we have to make use of the Clausius inequality in order to derive a working definition of entropy. Okay, now this is involved with derivation, guys. Okay, so I expect every one of you to fully understand how can we derive entropy from this Clausius inequality. Actually, not equity, inequality, inequality, right? Okay, now, let us assume you have a combined system which is made of a reversible cycle device and also a piston string device. Okay, so this particular combined system basically receive heat from high temperature reservoir. Let's say the temperature reservoir has a temperature of TR. Okay, and then basically from the four principle of heat engine, right, this thermal energy reservoir will supply delta QR heat into this particular reversible cycle. Okay, guys, remember because Q and also W, they are path function. That's why your D here, is in italic, to show that this is the path function instead of point function. Now, from the four principle of the heat engine, okay, this particular reversible heat engine will convert part of the heat it receives into work. So that's why you are the delta W reversible. Okay. Now, it also has to reject some amount of heat it received from the high temperature reservoir into a low temperature sink. So the amount of heat rejected is delta Q. Now, it happens that the amount of heat rejected from this reversible cyclic device, yeah, is being used or is being accepted by a gas inside this piston cylinder device. Okay, so when you receive heat from this particular reversible cycle, okay, let's say it has a temperature of T, where this temperature T actually represent the temperature of system and also the temperature at the boundary of this particular piston device, right? So when you have gas that receive heat, what happens is that it will expand. So kalau expand, you have boundary work. That boundary work, let's say we call it as delta W system. And this is just to differentiate between the reversible work produced by this reversible cycle device and also from this particular system. So that's why, as you can see from these two combined system, okay, so if we take into account from our energy balance analysis, guys, from the energy balance, okay, you are the energy in minus energy out, equivalent change of energy of the system. Now, if you look again from this particular combined system, right, the only transfer of energy involved on the left side of this particular equation, okay, you only have Q and W only, right? There's no mass transfer by heat transfer. And because here we assume this is a closed system. This is a closed combined system. So that means your punya mass is maintained within that particular boundary. So when you write down your overall energy balance equation, you have delta QR, heat received from high temperature reservoir, minus with actually this delta W, okay, is made up between delta and W's, actually we call it as delta WC, delta W for the reversible, plus with delta with W of the system. And so that's why we call it as WC combined. So that's why you have this particular equation over here. So on the right side of energy balance, here what we have actually change in kinetic, change in potential, and also change in internal energy. Okay. Now, guys, we assume that this combined engine is totally reversible. So what happened, guys, if you recall back from our last chapter, when you learn about thermodynamic temperature scale, remember that? Okay, we perform some sort of derivation. And so the outcome from there, you have this particular relation, QH over QL for reversible equivalent to TH over TL. Okay, so now if you look again from this particular diagram, okay, so you are the delta QR and then also delta Q. So what happened? We can make use of this relation and we apply that towards the combined system. And so that's why actually you are the delta Q. Actually what you have, okay, delta QR over delta Q equivalent DR over T. Okay, so rearrange because we want delta QR to be substitute inside our energy balance. Okay, so you are the delta QR equivalent DR times delta Q over T into this equation. So what we have is this particular expression. All right. Now, basically, you have delta W on the left side. We want to determine the work of the combined system. So that means we have to integrate the right side of equation. So that's why if I bring this delta D from the left side to the right side, it become integration. Now, your TR basically is just a constant value. So that's why, as you can see, the integration symbol. And then suddenly you add a circle in the middle of this integration to indicate that this particular integration process have to be performed over the entire cycle involved from this diagram over here. Okay? And then same thing also for integration of delta EC for the combined system. Now guys, basically the right side equation here and the delta EC is 0 and because it under a cycle or cyclic process. And because the other day we already proved that, for example, if you have like internal energy, right, between state 1 to state 4, and the resultant from there will give you 0. You can simply prove that during your punya free time over here. So that means you can simply get rid the expression of cyclic integration of delta EC, which is equal to 0. Now, what's left is this particular expression over here. Now, guys, remember, if we look again from this particular closest inequality of these two combined system, one you are the reversible cyclic device, another one just simply a system, an expression of system of a gas when it receives heat of delta Q. Now, if you recall back, guys, from the Kevin Planck statement of the second law. Remember, Kevin Planck statement ni is a special statement pertaining heat engine. Right? So, if you look closely from this combined system, remember, dotted line here represent the boundary of the system. This is where the area that we are interested to perform our analysis. So as you can see, the combined system receiving heat delta QR from high temperature reservoir, perform some part of the heat into work, and what happens is that you do not have actually a resultant delta QL over here. There is no delta QL over here. That means there is no low temperature sink that allow the system to expel heat in order to make the whole combined system function as a combined heat engine. So when that happens, okay, guys, so when that happens, your WC is not actually a value of net work produced. And then we know that, guys, for the work value, it must have positive, but now it cannot be positive. And so thus cannot be positive. You punya WC cannot be positive, right? But it can have, excuse me, it can have a, negative or even 0 value. Okay. Now, guys, let's have a look again from this particular expression that we have over here. Now, if your WC is, hold on, dr Q over T. Now, guys, we know that TR, yeah, represent the temperature of reservoir, and we know that TR value is always positive at all time because this is in Kelvin. Under the thermodynamic temperature scale, this is in Kelvin. That means positive always. Now, because your WC cannot be positive, that means it can take either negative or zero value, right? So guys, let's say if my WC is negative, whereas my TR here is positive, okay? So basically, guys, positive times with what to get negative? It must be negative for the delta Q over T, all right? So now, let's say for WC is 0, okay? Again, your TR still positive. So your punya cyclic integration of delta Q over T must be 0, right? So based from these two conditions that we have, so that's why I can simply say that my WC, yeah, which is equivalent to TR times cyclic integration of delta Q over T, must be always less or equivalent to 0 due to this particular reason. Right, so that's why, as you can see, this is an inequality expression pertaining the second law for the closest inequality. And this particular expression here is valid to all types of thermodynamic cycle, and whether you have reversible or non-reversible, including the refrigeration effect and also the heat pump system. Okay. Now, we still have yet to define the working principle or even link the entropy definition with closest inequality. Now, again, let's have a look on this particular closest inequality that we have derived earlier. Okay, the signage less than, this is inequality, right? If equivalent, that means this is reversible. Okay. Now, if we look from this particular criteria, if let's say, if I have the cyclic integration of delta Q over T is equal to 0, so that means this can only be happen if I have an internally reversible process occurred within the system. Right? So based on here, okay, what happens that I can know from this equation if your cyclic integration of delta Q over T for internal reversible is 0, that means my combined work for internal reversible also must be equivalent to 0. So what we can simply conclude that, right, the signage of equality inside this closest inequality that represent totally or just internally reversible cycles. Whereas the signage of less ni represent the irreversible one. Okay. Now, if we try to link this particular relation here with any existed property that we have learned earlier, like enthalpy H, specific volume, and some other properties that we can extract values from the thermodynamic booklet, it seems that it is almost impossible because none of that actually satisfy the criteria. Okay, so for example, let's say from this volume change or even specific volume change inside a piston cylinder device. Okay, So initially, dia punya volume is 1 cubic meter. So when expansion, so your punya V2 has become 3 cubic meter. Now, when you compress the system, meaning that when we try to reverse back, apa ni, you reverse it apa ni in quasi equilibrium manner, so it become reversible. So here V1 3, V2, sorry, V1 is 1, V2 is 3, and then when you compress, it will go back to its initial state of 1 cubic meter. So now if we take into account on the whole process, so if we want to find the change in volume for this particular cycle, or even the cycle integration of your delta V, that will result in 0. Okay, so this does not actually satisfy the needs for this particular closest inequality, right? So again, let's try some other example. Let's say we take into account on the W component, W net. Okay, so let's say from this figure again, right? This is an expansion. Let's say expansion process, okay, that will produce to, let's say, around 3 kilojoule of work produced by the system. Now, to restore back into its initial volume of 1 cubic meter, the same amount of work has to be supplied. So that means minus sebalik with 2 kilojoule. So the result from that will give you 0. So that means kalau you punya W net here is 0, and then we try again to apply on this particular closest inequality, again, it does not work. So that means it has to be something different and then the already existed property that we have made use or learned before. So that's why during that time, Clausius, he claimed that he has discovered a new set of property, and he has choose that particular property to be called as entropy. Okay, so now he has assigned the symbol S as the entropy, and then that's why he made use of delta S equivalent to delta Q over T for irreversible. And of course, from this unit, you can see Q has unit of energy and then temperature. Remember, expressed in terms of thermodynamic temperature scale. So that means the unit is in Kelvin. So entropy has a unit of kilojoule per Kelvin, right? We can actually determine entropy change of system by make use from the original equation of entropy here, right? So you put lah delta S, or even the triangle, or even delta S. Actually, they are both same. So we have to consider the difference between final and initial state of the process by integrating delta Q over T for internally reversible. So if case you want to find your punya delta S, so you are the cycle integration of between state 1 to state 2 and delta Q over T for internally reversible. Okay, remember that just like in any properties that we have learned earlier, okay, the S value here actually represent the point function. S is your punya point function. So that's why if you want to measure delta S, let's say from this example, dotted curve here represent irreversible, whereas solid curve here represent reversible process. So your change in delta S, whether reversible or irreversible, both will give you the same answer or same value of entropy change of the system. Because your entropy is a point function, as what I have mentioned earlier. Okay. Hey guys, so far any question? Anything that you want to ask? Okay, good. I presume no. Everybody fully understood and on the derivation from the closest inequality until you get the definition of entropy as. Right. Let us move along. Okay, now, there is a special case, which is called internally reversible isothermal heat transfer process. Okay, so looking from this original equation here, okay, integration delta Q over T for interreversible. Now, if you have an isothermal, so that means you punya T is constant. So that's why you can simply say that T1 equals to T2, or even you can simply call it as T naught in general. So when that happens, your T here constant, let's say we call it as T naught, right? So when you integrate this particular expression, right, you can bring the constant outside from the integration. So when you integrate 1 times with delta Q between state 1 and state 2, so in the end of the day, you have delta S equivalent Q over T naught. Okay, guys, you might wondering, what is the use of this particular expression? So actually, this is very useful when you try to determine entropy change of, excuse me, entropy change of thermal energy reservoir. Kenapa? If you recall back from criteria of any thermal energy reservoir, those are the bodies that be able to absorb or even supply heat, without experiencing significant temperature change. So that's why, right? Most of the time, if let's say you get rid of heat from your heat exchanger into nearby river or water, basically that river will not experience any change in its temperature. It will remain constant at all times. Okay, so that's why you can find the entropy change of any reservoir by make use of this particular formula. Okay, if you look from this example, you have piston cylinder device contains liquid vapor mixture, water at 300 Kelvin. During constant pressure process, 750 kilojoule of heat is transferred to the water. As a result, part of the liquid in the cylinder vaporizes. Determine the entropy change of the liquid vapor mixture of water during this process. Okay, so guys, what happened? This is like you punya piston cylinder device. Okay, so here you ada like some sort of heat transfer. Okay, so that means you ada Q in into the system, you punya boundary, and then as a result from that, the system will expand. Okay, now to determine entropy change, right? Remember, system is inside the mixture inside this piston device. It receives heat. Okay, so the amount of heat received is 750 kilojoule. Okay, now the temperature, right, is at 300 Kelvin because the 300 Kelvin is the amount of heat which is constant received from an external source over here. It can be probably from, of course, from a reservoir. Okay, so basically your like Bunsen burner ni can act as your punya reservoir or even the heat source that supply heat and also the temperature, which is the temperature inside this particular system. So from there you simply calculate lah. Then you can get you punya answer berapa. So probably it's around 2.5 kilojoule per Kelvin from there. Okay, let's move on to the increase of entropy principle. And this is very important. Yep.
I have a question.
Yeah.
What the system gain heat and release heat?
Gain heat and release heat at the same time, you mean?
Yeah.
Then we have to look at on the resultant, the QNet.
QNet, okay.
Probably,
Yes.
let's say during a process, and you have like, let's say from state 1 to state 2, and you are the Q in, and then suddenly from state 2 to state 3, you are the Q out. Now, to know the overall, so that's why you can add the QNet to know the direction of flow. Is it totally inside the system ataupun actually leaving the system? So from there, and you can simply calculate whatever delta S or some other property definition from there. Okay, yeah?
Okay.
All right. Okay, increase of entropy principle. Now, let us consider from this figure here, state 1, state 2. Now, state 1 undergo a process. It can be reversible or irreversible. Whereas from state 2 to state 1, this is to restore back the property of the state back to its initial state. So it undergo at internally reversible. All right. Now, if we take into account from your punya closest inequality, right, we have cyclic integration of delta Q over T equivalent or less than 0. Okay, so this is your starting inequality. Now, we have the symbol of circle inside here. That means we have to consider all processes from process 1 to 2 or even from 2 back to 1. So that's why when you express this thing according to the processes, that's why on the left side here, you have integration of delta Q over T plus with integration from state 2 to state 1, delta Q over T for internally reversible. Because remember, only from state 2 back to state 1, you have internally reversible. Again, equivalent less than 0. Now, if you simplify, you can simplify this equation, you will end up with delta S equivalent or greater than delta Q over T. All right. As usual, the equivalent sign represent internally reversible, whereas the greater sign holds for the irreversible process. Okay. Now, if we look closely from these two terms here, okay. Now, the left side equation, delta S, represent entropy change. Whereas on the right side, represent the entropy transfer by heat transfer. So that means this is mechanism of entropy transfer. So looking from here, it looks like there are some sort of entropy which is being created in order to balancing back this particular inequality. Right? So that's why we can say that the inequality sign indicates the entropy change of a closed system during an irreversible process is always greater than entropy transfer. Okay, so when that happens, from your equation that we have derived earlier, from from here. Okay. And then we take into account on the entropy being created or generated during an irreversible process. So entropy change of the system equivalent to, let's say S2 minus S1, equivalent to the integration of delta Q over T. This represents the mechanism of entropy transfer by heat transfer plus with S gen. Okay, remember that the S gen always have positive value or zero. Okay, it depends on process and it is not a property. Why it is not a property? Because one thing for sure, if you check from your thermodynamic booklet, you cannot find any S-gen value. So S-gen has to be calculated manually. Right? Remember, S is not equivalent to you punya S-gen. Remember that. S is entropy. S-gen represent entropy generation due to the presence of irreversibilities effect inside the system. Okay. Now, guys, let's say if you have an isolated system. Okay, we know that basically when you have an isolated system, that system is being covered by some sort of insulation material in order to prevent any heat transfer into and out of the system. And also at the same time, your punya mass remains constant, right? So when that happens, okay, from this equation here, from the increase of entropy principle here, delta S greater or equivalent to delta Q over T, Q0, that's why you punya delta S for an isolated system is always greater or equivalent to zero, right? So this equation here actually is the working definition for your second law. And that's why this particular relation here is known as the principle of increase of entropy, right? Now, it's stated that total entropy change of an isolated system during a process always increases. Or in the limiting case of a reversible remains constant. Remain constant, that means equivalent to zero. Always increases, that means greater than zero. So reversible represent the ideal case, whereas when your entropy system of isolated keep on increasing, that means we are dealing with the actual cases, right? So that's how actually you can differentiate between the actual and also the ideal case of an isolated system over here. Okay, guys. If you look from this figure, you are the system and it close surrounding, right? Excuse me. Sometimes the system and also is close. I'm talking about close. Surrounding can be categorized an isolated system boundary. Okay, all right. You still have transfer of heat and work into and out of this system, right? Because the surrounding here will not experience any mass flow or even mass transfer, okay? And there's no Q and there's no W exchange between this particular closed surrounding and also the outside part, because this particular isolated system has been categorized as adiabatic. And so here you are the insulation layer to make it adiabatic, right? So when this happen, when you try to write down again in terms of your entropy change of the system, okay, your delta S actually consists of delta S for the system plus also with delta S of this closed surrounding, okay, should be greater or equivalent to 0. Now, because you have an adiabatic system, and this is part of your punya isolated system like this one here, this equation here must be equivalent to your Sgen. So in other words, your Sgen must be equivalent to the change of entropy of the total system, which is made of the system itself plus with closed surrounding must be greater than 0. And of course, and the signage of greater represent the irreversible, whereas the equivalent represent the reversible process, right? Okay, so what we can simply summarize from this increase of entropy principle, right? When you perform your calculation, okay, when you calculate your Sgen, when it is greater than 0, that means you have an irreversible process. That means you have other actual. But if your Sgen is equivalent to 0, that means this is a reversible. And of course, reversible ni can only obtain under ideal or theoretical, right? And then kalau you punya Sgen is less than 0, this is impossible because remember back, your Sgen is always positive or 0. So kalau you have a calculation that gives you negative, that means something is wrong over there. Tak logic to represent the entropy change of the system. Right. 3 important remarks that we can simply summarize regarding on the entropy. Of course, because this entropy ni related with the second law. Okay, so definitely we know that processes can only occur in certain direction only. And it has to follow from your Sgen greater or equivalent to 0 and based from the increase of entropy principle. Secondly, entropy ni is non-conserved property. So that's why there is no such thing as conservation of entropy principle, right? But energy, yes, is conserved. That's why you are the conservation of energy principle, right? And thirdly, the performance of engineering system or devices, we know it's being degraded with the presence of irreversibilities, such as friction, incomplete combustion, incomplete reaction, mixing, and so on. So the entropy generation and the Sgen that you have earlier is a measure of the magnitude of the irreversibilities present during a process. That means your Sgen, when you calculate, if it is bigger, that means greater than 0 of 1,000, that means it indicates how severe does the system being affected due to the presence of irreversibilities. And the greater the value, that means more irreversibilities present inside the system or process. Okay, hey guys, any question? Okay, so kalau silence, I presume everybody understand. Good. Right. Let's have a look from this example. Okay. A heat source at 800 Kelvin loses 2000 kilojoule of heat to a sink at A, and that sink too has 500 Kelvin temperature, and then B, the sink B2 has temperature of 750. Now, determine which heat transfer process is more irreversible. Okay, okay, guys. We know, basically what happens is that source will provide heat to a heat engine and perform a job. But this time there is no circle in the middle, and because this time the heat which is supplied by the source is being directly channeled to the nearby sink to see what happened. How does the severe of the irreversible can actually affect the amount of heat transfer process. Okay, let's say we perform first for part A over here. All right. Now, temperature sink is at 500. So that means we perform, okay guys, first of all, our system consists of high temperature source and low temperature sink. So this is like a combined system between these two. So in order for us to find our delta S gen, all right, guys, if you look again from previous equation, this is what we have earlier. Okay, so we make use of that formula. Then equivalent change of entropy between source and also sink. So that means we have to evaluate delta S for source and also delta S for sink. All right. Now, this is where you have to make use of, remember from this internally reversible isothermal heat transfer process. This formula, because our T naught is constant for the temperature source and also for temperature sink. So that's why, let's say for my delta S source for for part A here, Q source over T source. Guys, remember Q source, right? This source here is losing heat from the system. So that's why I have a minus signage from my Q source. Okay, temperature, remember the temperature of the source is at 800 Kelvin. So from there, let's say minus 2.5. Now, when we perform entropy change for sink A, and again Q sink over T sink. Now, sink receive heat from high temperature source. So that's why this time I add a positive value of 2000. Okay, divided by the temperature. So that gives me 4, positive 4. Now, total, that will give you 1.5 kilojoule per Kelvin. Right? Now, we repeat again the same method of calculation and for the sink at 750. So guys, from there, let's say this is the value, right? The data as source ni unchanged because temperature the same and also the amount of heat is expelled also the same. Only your punya sink B temperature that differs. So data as sink positive 2.7. So when you summarize this, okay, 0.2 kilojoule per Kelvin. So guys, can you tell me between these two values here, which process is more irreversible? A. Semua betul A ke ni? Salah jawapan tu. Bukannya A. Why did I say wrong for A? Because Sgen is the measure of irreversibilities present inside a system or a process. Okay, the greater the value of Sgen indicate there are more irreversibilities present within the system or process. Now, because you punya B is lesser than your punya part A, so that means yes, of course your punya part A tu is more irreversible compared than B. Sorry I thought nampak macam B ni. Okay, regarding on entropy change of pure substance. Okay guys, because just now we have defined entropy, and entropy ni is one of the property, and its value is fixed one, the state is fixed. That means this is a point function. Okay, so that means in order for us to make use or even extract entropy value, right, from property tables, you have to make use similar method as what you have learned in chapter number 3 the other day, regarding on the property of pure substance. All right. So as usual, guys, kalau let's say you have a mixture, so that means you have to make use of the property tables. Let's say if you given temperature and also the X, you can find what is your punya average over here kan. Whereas if you have like superheated, okay, so you refer to superheated table to get your punya S3 for example, and then if it is under compressed liquid, which is in the left side of the region, so you have to make use of the compressed liquid table. And remember that, guys, if you are given pressure and temperature, because compressed liquid is temperature dependent, so you kena make use of the temperature T1. So you have to make use of temperature T1 in order to get you punya S1. So S1 ni must be equivalent to your punya SF at given temperature, not pressure. All right. Okay. When we talk about entropy, right, normally when we represent a process on any phase diagram, okay, it will be appropriate that to have one of the axis is in the entropy axis. So here, for example, temperature versus entropy. This is your punya saturation curve. All right. Okay, guys, under T versus S diagram, okay, we can have the constant pressure trade line as well as constant specific volume trade line. Okay, so if you look closely between the constant pressure and constant specific volume trade line, you can see that the constant specific volume trade line, the gradient is more steeper as it approaches this saturated vapor line. Okay, but still within this mixture region, all right, the gradient slightly decrease, but higher compared than your punya constant pressure trade line, because inside this mixture, the P constant ni is horizontally drawn between ataupun horizontally connected between your saturated liquid and saturated line over here. All right, and of course, guys, you can see that actually this line can be simply extended to include the process for the compressed liquid and so on for both constant pressure and also constant specific volume lines over here. Okay, now from example 3, you have rigid tank, contains 5 kilogram of R134A. Initially, T1 20 degree and P1 140. This refrigerant is now cool while being stirred until its pressure dropped to 100 kilopascal. So this is your P2, the main entropy change of the refrigerant during this process. So now refrigerant 134A is one of the pure substance. And then from what we have learned earlier in other slide, and to find the entropy change of the R134A, basically you have to consider the entropy at the final state minus with the entropy at the initial state. Okay, so guys, like what I have mentioned earlier, I expect every single one of you until this chapter to master yourself in performing checking and also extracting value from booklet. There's no time anymore to do or show to you one by one the step on how can we get the values. So from here, guys, so given P1, T1, and of course you have to perform checking first, right? So guys, can you tell me what is the state of R134A initially? Can you please check your table? What is the state? Remember, this is R134A, bukannya water. Anyone? Some of you request a break. Okay, I can understand that. Let us finish first with example 3. Okay, let's say I open to table A11 using temperature as my independent property, right? So um, from table A11, so bila T1 equals to 20 degree, P set equals to 572 kilopascal. So obviously my P1 is lesser than P saturation, right? So kalau that thing happen, that means I ada superheated. Super vapor. So refer to table 18 from here, right? Now, because you are the rigid tank, so state 2 must share the same specific volume over here. So you are the P2 given and V1 determined from earlier step. Then from table A12, because pressure given, to compare the VF and VG. So in between. So that's why you are the mixture. Kalau mixture, that means involved with determining of quality X from there. Okay. So bila once you got you punya X2, then you can get what you punya S2 from there, right? Then simply substitute into your entropy change. So you have negative value. Guys, why does I have negative value? Why? Why negative? Cool. Okay, actually, to be more precise, and the refrigerant is losing heat to the surrounding, right? So if the system is losing heat, that means Q transfer into the surrounding. That means it will carry along its entropy value as well, right? So as you can see, when the system is